Welcome to my presentation on the multi-user security of the Elephant v2 Authenticated Encryption mode. This is a joint work with Tim Bijne, Yulong Chen and Christoph de Bruinig. The work is about authenticated encryption, and let me start by recapping the basic idea of authenticated encryption. Authenticated encryption is nothing more than a mathematical function technically. It's a function that gets as input a key, associated data A and a message M, and in addition it gets a nonce, and it outputs a ciphertext and a tag. And its goal is to use the secret key to encrypt the message M to obtain the ciphertext, and the tag, the goal of the tag is to authenticate the associated data and the message. And the main goal of the nonce here is to randomize the scheme. Associated with this authenticated encryption function is an authenticated decryption function AD that gets as input the key, the nonce as before, associated data as before, and now it gets as input the ciphertext and the tag, and it outputs the message M if the tag is correct, and it outputs nothing otherwise. AE and AD should satisfy two main goals, namely that if you encrypt under a certain key and nonce and associated data a certain message, you will get a ciphertext and a tag, and if you feed those data back with the same nonce and associated data to the decryption, you should get the original message M back. Authenticated encryption is a very popular design, a very popular symmetric cryptographic primitive, and recently the NIST, the National Institute for Standards and Technology, launched a competition for the design of a lightweight cryptographic authenticated encryption scheme. As a matter of fact, they asked for authenticated encryption and optional hashing. The submission should achieve a minimal level of 2 to the power 112 security. So the scheme should achieve at least 112 bits of security, at least if the attack complexity, the data complexity, is at most 2 to the 50 bytes. The competition was started officially in February 2019 with the submission of 56 first round candidates. In August they went to the second round with 32 second round candidates, and in March of this year they went to the final round with 10 finalists. And one of these finalists is Elephant. So Elephant is a third round candidate by Bijne, Chen, de Bruinig and me, and it's a permutation based authenticated encryption mode. However, unlike the more conventional permutation-based authenticated encryption mode, Elephant is parallelizable. So it's different in the sense that it allows for parallelization. And as a matter of fact, Elephant was designed with the main goal to achieve an authenticated encryption mode that achieves the smallest possible cryptographic permutation, while still meeting the security strength dictated by the NIST call for submissions. And the design of Elephant is really simple, and this is the Elephant v1 design, which was used in round 1 and round 2. So we have a cryptographic n-bit permutation, and we define a mask function that on input of a key and two mask parameters A and B permutes the key to get a subkey, and then evaluates the LFSR phi1 or phi2 a certain number of times on this input, depending on the values A and B. And the design is simple. So we first start with an encryption part where you have the nonce, and this nonce n is served as input to all permutation calls, where the input and the output is masked using mask k 00 up to mask k LM-10, where LM is the number of message blocks. So you use B as 0 in the mask, and A runs as a counter for the number of message blocks. The message is then padded into blocks and added to the ciphertext. So this is basically a counter mode with a masked permutation. Then we have associate authentication, so we glue together the nonce and associated data and injectively pad it to n-bit blocks A1 up to LA. The ciphertext is also injectively padded to C1 up to CLC, and we again use this mask permutation, but then with different parameters A and B. So for the ciphertext portion, we take B as 1, and A still runs from 0 to the number of blocks. For associated data, B is 2, and A runs from 0 to the number of blocks. All of these outputs are added, and you truncate to T bits to get a certain tag. From a high-level perspective, Elephant V1 is an encrypt then MAC design. So you first encrypt the message to get a ciphertext, and then you compute the tag. And this is known as one of the most secure generic authenticated encryption modes because it achieves ciphertext integrity. Encryption is done using counter mode, and authentication is a Wigman-Carter-Shoup variant, where I recall that the first associated data block contains a nonce. It uses a single cryptographic primitive P, and it only uses it in a forward direction, which means that for encryption and decryption you never need the inverse of P. The masking is chosen in a very smart, in a subtle way, in such a way that the updating can be done efficiently. In particular, if you have a certain mask, in this case mask 00, you can easily go to the next mask by evaluating phi1 on the value. So generally mask on parameters I0 is simply the mask of I minus 1, 0, evaluated by phi1, where phi1 is the LFSR. And the same holds for the bottom portion. A different trick is that if you take the mask for encryption and mask for authentication and you simply add them, it turns out that you get exactly the next encryption mask. So far so good. This was Elephant V1 for round 1 and round 2. And Baena et al. At FSC, the special issue for NIST competition schemes, they proved that Elephant V1 achieves AE security, so confidentiality and integrity, up to around 4 times sigma times p divided by 2 to the n, where sigma is the online complexity, so the number of data blocks that are authenticated and encrypted, and p is the offline complexity, roughly corresponding to the number of primitive evaluations that the attacker can make. They proved this under the assumption that p is a random permutation, that phi1 is maximal length, LFSR, and that the attacker cannot find any pairs AB and A prime B prime such that you have 2 times the same function. Phi2 to the B after phi1 to the A should not equal to phi2 to the B prime after phi1 to the A prime. This in fact corresponds to computing the discrete log of phi2 with respect to phi1. And finally, this proof was given under the assumption that the attacker is a nonce-based adversary. The cool thing of this bound is that it in fact showed that the parameters, the security parameters of the NIST lightweight call, can be met with a 160-bit permutation, and this is the smallest possible permutation that you can use to achieve the NIST security parameters. And Elephant also uses a 160-bit permutation. Okay, so far so good, but now for the third round, NIST Elephant went to a different scheme. So they made some changes, and they now ended up at Elephant V2. And it looks similar. In fact, the masking is also similar, but there are 2 subtle changes. One of the changes is that the permutation here, the mask permutation evaluation corresponding to A1, is not anymore done at A1, but instead it's moved to the end. So first you add all other values and then you do the masked permutation evaluation. A second change is in the parameter rules of the masking. In fact, the value B is now different. Note that for Elephant V1, for encryption we had the value B is 0 and now it's B is 1. For associated data, for the ciphertext authentication we used to have B is 1 and now it's B is 2. And for associated data we used to have B is 2 and now it's B is 1. And the reason why this is done is that this finalization now is done for mask 0, 0, and it's slightly more efficient than if you take mask 0, 2. So this is just an elementary change, nothing spectacular. The fact that we moved this primitive here is more subtle. And the reason why this is done is, as claimed by us when we did this, that version 2 retains all good properties of v1, and in particular v2 still achieves authenticity and confidentiality under nonce-respecting adversaries. In addition, it turned out we claimed that this scheme also achieves authenticity under nonce misuse. No confidentiality, but authenticity. And the trick here is that we moved from a Wigma-Carter-Shook mode to a protected counter sum mode. So you have a counter value here, the bottom line, and that one is protected by this call. However, this only stayed at a claim, and now in this work we prove security of counter mode. So in a nutshell, we proved that the security guarantees of Elephant v1, namely confidentiality and authenticity against non-space adversaries, is preserved. In addition, we proved that Elephant v2 indeed achieves authenticity under nonce misuse. And as a matter of fact, we proved that these even hold in the multi-user setting. And most importantly, the security bound does not really degrade if the attacker can attack multiple schemes, as long as the number of schemes that the attacker can attack is somehow limited. More technically, these are the results we prove. So we again prove AE security against nonce respecting adversaries under the same assumptions as before, up to 4 times sigma times p over 2 to the n. So the same bound, roughly the same bound, so we simplified it for the sake of the presentation. But now we have multi-user security where the attacker can attack multiple mu instances of the scheme. And this mu turns out to influence only minor terms in the bound. In addition, we prove authenticity, multi-user authenticity up to the same bound, but now against attackers B that might reuse nonces. So we achieve nonce reuse authenticity, and both in the multi-user security setting. I will not discuss the proof, so for the proof, please refer to the paper. I will only give you the very high level idea. And at a very high level idea, so we have this scheme. The difference with the previous picture is that now we have multiple keys, k1 up to k mu. And this is the picture for the ith instance where you have key ki. And ki goes into the mask, and for the rest it's all the same. Now the first step is to, again, just like for Elephant v1, isolate what we call the simplified mask Evan-Mansour construction. Note that if the mask would be secret, this would be secret in the same. This would be an Evan-Mansour construction, but now we have a masked Evan-Mansour construction in terminology of the scheme of Granger et al. 2016. And this is what we call tweakable block cipher. And we isolate this tweakable block cipher building block, and we prove multi-user security of this building block. And the proof is comparable to the single-user security, except that now we look at multi-users, but it doesn't have a major influence on the bound. But once we prove that this building block is multi-user secure, we can replace it by secret permutations, which differ depending on the tweak. And in this case, the tweak consists of AB and the value I. So we replace these boxes, all these red boxes, by different permutations, which differ for the choice of AB, the superscripts, and I, the subscript. But now we ended up at mu basically independent instances of Elephant v2. Those are all independent, and the attacker can evaluate multiple of them, it can evaluate mu of them, but they are all independent. And this means that we can simply consider mu independent single user adversaries with joint complexity sigma p, and then we can sum over all these mu independent adversaries, and then we get our bound. So we have to focus only on a single user case. So far so good. We could technically then maybe rely on the existing proof, but the difference now is that we moved this building block here to the end. So we have a different authenticator. So we have to redo the proof of the Elephant v2 mode here. And then but the basic idea is the same, that we have encryption, which is nonce based. This is just counter mode based on the nonce, and if you repeat the nonce you have insecurity. So confidentiality, the encryption portion, is secure only against nonce-respecting attackers. For authentication, you have a nonce here, so nonce is the first part of A1, but it doesn't influence the security. So this scheme is even secure under nonce misuse. And this is how we proved security in a nutshell. To conclude, so Elephant v1 already achieved excellent security, so confidentiality and authenticity under against nonce-respecting attackers. We proved that Elephant v2 preserves all these security properties. So v2 preserves all good things of v1, up to a comparable bound. In addition, it achieves authenticity against nonce misuse attackers. So if you put this in a cool table, we have Elephant v1 that achieved confidentiality and authenticity in the nonce-respecting setting. Elephant v2, as we proved now, achieves confidentiality and authenticity in the nonce-respecting setting, and in addition it achieves nonce misuse security. And finally, these results hold even in the multi-user setting, where the number of users, as a matter of fact, only has a minor influence on the security bound. And that concludes my presentation. Thank you for your attention.